Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.3. How derivatives affect the shape of a graph.
Lesson 1. Where is f increasing or decreasing?
In this section, we're going to learn how the derivatives of a function, in particular f prime and f double prime, affect the shape of the graph of that function. And in order to do that, we have to go back and remember a little bit about functions increasing and decreasing. We've already talked about when a function increases and decreases earlier in the course, but here we want to write down a very technical definition of what we mean by a function increasing or a function decreasing. So let's look at this little paragraph up here at the top. It says a function is increasing on an interval if the outputs are getting larger as we move to the right. That would be a kind of intuitive definition. We usually say the graph is going up as you move to the right in the positive x direction. Well, if you think about it, that means that as we go from a smaller x value, I'm going to call that x1, to a larger x value, call that x2, something happens to the outputs. x1, you notice if I plug it into the function and get an output on the y-axis, here's my f of x1, that's really this height on the y-axis. That's the same as this height on the graph. So I'm going to call that f of x1. And x2, if I plug it into the function and get an output value on the y-axis, f of x2 would be this distance on the y-axis, same as this distance over here. And so the height of the graph at x2 would really be f of x2. So when my x2 is to the right of or greater than x1, what can I say about how f of x2 compares to f of x1 if I have a function that's going up? So let's go ahead and write that down. x2 is bigger than x1. Well, if f is an increasing function, that would mean that f of x2, the height under the graph here, is bigger than f of x1, the height under the graph at x1. And that's really the technical definition of a function being increasing. We say a function is increasing on an interval if whenever x2 is greater than x1, it implies that f of x2 is greater than f of x1. So as we move to the right on the graph, these outputs are getting larger. Same type of idea, a function is decreasing on an interval if the outputs are getting smaller as we move to the right. That would be a kind of intuitive definition of what we mean by a function being decreasing. As we move in the positive x direction, the function is falling, the outputs are getting smaller. Let's look at what happens to the output values the way that we did up here. At x1, the height is f of x1, and I could go ahead and just write that in here, f of x1, and at x2 we have a height under the curve, f of x2, and we can see that if it's a function that is falling, these heights are going to be getting smaller. Same thing as saying the output values are getting smaller as we move to the right. Well, let's try to fill in this box. If x2 is greater than x1, in other words, x2 is to the right of x1, how does f of x2 compare to f of x1 if we have a decreasing function? We can see that f of x2 is going to be smaller than f of x1. So we say more technically that a function is decreasing on an interval if for each x1 and x2 in that interval such that x2 is greater than x1, x2 is to the right of x1, the outputs are getting smaller f of x2 is less than f of x1. So this height is smaller than this height. And that's a little bit more technical definition of a function being a decreasing function. Okay, I want you to think about this example down here, and the question is, where is f increasing and where is it decreasing? And when we say where, we really mean on what x intervals. So what I'd like you to do is pause the tape for a moment and try to write down the intervals on which f is increasing and the intervals on which f is decreasing. And by intervals, I mean intervals on the x-axis. So do that, and then we'll go ahead and go through it together. So restart the video when you're ready. Okay, so let's think about where f is increasing. We're really just looking for where the function is going up as we move in the positive x direction. And this arrow indicates that the curve goes on in the same manner forever in this direction. So it looks like as we come in towards x equal 4, the curve is going up as we move to the right in the positive x direction. So this function would be increasing all the way from minus infinity up to 4. Now you might be tempted to put a rounded parentheses here, and oftentimes we will put a rounded parentheses, but it's actually a little bit sloppy. Really, we should put a square bracket here, and the reason is that the technical way that we have defined a function being increasing is we talk about a function being increasing on an interval of values, and it turns out that on the interval from negative infinity up to and including 4, if I choose any x values, including 4 itself, and call the first one x1 and the second one, I let 4 be equal to x2, then when x2 is greater than x1, it's true that f of x2 is greater than f of x1. So it's kind of a side remark, but technically we should include this endpoint value because we define a function being increasing not at a point but on an interval, and it's really increasing then on that half open interval, so that I include the endpoint 4. If you put a rounded parentheses, I don't think your instructor is going to mark you off for that. Okay, is there anywhere else where you found that f was increasing? It looks like it's not increasing in here, it's flat, but then from 11 to 15 the function's going up again. So we could say and, or you could say union, or you could just list the intervals on which it's increasing. So it's increasing on this interval, negative infinity to 4, and also from 11 to 15. And again, you can include those endpoints, and that's just because of our technical definition being a definition of f increasing on an interval rather than at a point. How about f decreasing? Well, it looks like f is decreasing. It's going down from 15 onwards, and this arrow indicates that it continues to do the same type of thing. It doesn't do anything weird like turn around and come back up later. So we could go ahead and say that the way this function is drawn, it is decreasing from 15 to positive infinity. Well, that really answers this question, but you might wonder, hey, we missed an interval. What about this interval between 4 and 11? Is f increasing on that interval, or is it decreasing on that interval? Well, actually, it's doing neither. It's staying flat. It's staying constant. So you might notice that f, we say, is constant, meaning it's not rising, it's not increasing, it's not falling, it's not decreasing. We say f is constant on the interval from 4 to 11. Okay, so now we've talked about what we mean by a function increasing and decreasing, and we've even talked about the kind of precise mathematical definition of that. What I want us to do next is to turn to the next page and just think about a certain situation. So we're going to think about this situation, a situation where between a and b on that interval, the slopes of the tangent lines to my graph, so we're going to graph y equals f of x, the slopes of the tangent lines are all positive. on that open interval from a to b. So let's think about that situation. The slopes of the tangent lines are all positive. What does that mean? It means that if I pick out particular points between a and b, I've picked out 4 of them, but we're really saying at every point between a and b, the tangent line slope is positive. That means that the tangent line has to have a slope that has to be a line that is going up, rising, as you move to the right. So the picture would have to look something like this at any point that I choose between a and b. And we can ask the question, well, what kind of function f would have a graph that would have these as tangent lines, so that all of its tangent lines were positive? And the only kind of graph that would fit with that, I hope you can see that, is one that's going up as we move to the right. It might wiggle around a little like this, but it couldn't start down, or else you would suddenly have a tangent line that had a negative slope to it. So if the slopes of the tangent lines are all positive on the interval from a to b, it would mean that my function is going up as I move to the right on that interval from a to b. So it would mean that f is increasing on the open interval from a to b. By the same token, suppose I told you that between a and b, I had a graph of a function f whose tangent lines were all negative on the interval from a to b. I've just shown 4 points between a and b, but we're really saying that every point between a and b, I have a tangent line whose slope is negative. Well, that would mean that the tangent line would have to be falling as I move to the right. So I would have to have tangent lines that are going down as I move to the right. And what kind of graph would f have to have so that it would end up with these as its tangent lines? The only kind of graph that would work would be one that is falling as I move to the right. In other words, f would have to be a decreasing function on the interval from a to b. So I'm just going to write that in here. If the tangent lines are all negative on the interval from a to b, it means my function must be decreasing on the interval from a to b. So I hope that kind of makes sense intuitively. Positive tangent lines, well, the only kind of function that could have positive tangent lines would be one that's increasing. Negative tangent lines, well, the only kind of curve that could have negative tangent lines would be one that is decreasing. So let's summarize that in a little theorem here. I say if f prime is greater than 0, and remember that f prime is exactly the same as the slope of the tangent line. So what we're saying is the slope of the tangent line is greater than 0. In other words, is positive. So when we say f prime of x is greater than 0 for all x in the interval from a to b, we're really saying the slope of the tangent line is positive for all x in the interval from a to b. And we just got through saying if that was true, it meant we had an increasing function. It means that the tangent line slopes look like this, and so the only function that can go along with that is one that is increasing. So we could go ahead and say f is increasing on that open interval from a to b. And if f prime is negative for all x between a and b, well, that means the slope of the tangent lines are all negative between a and b. And so that's the situation we talked about here. You've got tangent line slopes that are less than 0, that are negative. The only kind of curve that could go with that is a curve that is decreasing. So we could go ahead and conclude f is decreasing on the interval from a to b. Well, suddenly we have a way of knowing exactly where a function is going up and where a function is going down. If we don't know anything about the function's graph, all we know is the equation of the graph. If we find its derivative, anywhere where the derivative is positive, we know that the graph of f must be going up. And anywhere where the derivative is negative, we know the graph must be going down. So it gives us an enormous amount of information about the graph of f. It tells us exactly where it's going up and exactly where it's going down and exactly the points where it is switching from going up to going down or from going down to going up. Okay, let's go ahead and look at our next page, and there we're going to look at a specific example. And let me tell you a little bit about how the pages work in this particular section. Right now we are talking about the effect of the first derivative, f prime, on the graph of the original function f. And in a little bit later in this section, we will go back and talk about the second derivative and how it affects the graph. So we're going to look at 3 examples in this section. This is going to be our example 1, and we're only going to do part A of example 1 to start with. That has to do with where the function is increasing and decreasing. And we'll do part A on each of the 3 examples. So we're going to do example 1 part A, we're going to flip forward and do example 2 part A, and flip forward again and do example 3 part A. Then we'll go back and discuss some more stuff, and we'll come back to our 3 examples and do parts B for all 3 examples. We'll discuss some more stuff in general, and we'll come back and do parts C and D of all 3 examples. So that's just to give you an idea of how we're going to work through this particular section. So there'll be a little bit of flipping back and forth, but I think you'll be able to follow quite easily. Just remember there are 3 main examples that we're working on, and here's the first one. Let's suppose f of x is this function, 3x to the 4th minus 4x cubed plus 1. You might notice right away what type of function this is, and later on in later sections where we kind of really practice everything we learn in this section and really practice graphing functions, we'll talk more about types of functions. But what type of function is this? This is a polynomial. So just kind of keep that in the back of your mind, because remember, we do know some things about polynomials and their graphs. We know that a polynomial is continuous everywhere, so it couldn't be a graph that has like a vertical asymptote in it, or a hole in the graph, or a jump discontinuity, or even a removable discontinuity. A polynomial always has a continuous graph. It's continuous, and it's also what's called smooth, which means it doesn't have any sharp corners or cusps in it, but that's something that we'll discuss later. But we do know that a polynomial is always continuous, and so that's nice. We know there aren't going to be any weird breaks or graphs or vertical asymptotes that we have to worry about. So keep that in the back of your mind. But what we're concentrating on right now is just part A in all of our examples. And part A says, where is f increasing, where is it decreasing? And when we say where, again, we mean on what x interval is it increasing, and on what x interval or intervals is it decreasing. Well, we just go through saying that to decide where f is increasing or decreasing, really all we have to do is look at its derivative and at the sign of that derivative. So let's go ahead and find the derivative of our function. So I'm going to find f prime of x, and let's see, that's easy to do. So I get 12x squared minus 12x cubed, if I can get that right, minus 12x squared. You were probably shouting at me there. So f prime is 12x cubed minus 12x squared, and derivative of 1 is just 0, so that drops out. So we're wondering where this expression is positive and where it's negative. Well, it's a little hard to see where it's positive and negative in this form. Let's go ahead and factor it, and I think it will be easier. So it looks like there's a common factor of 12x squared that I could pull out. What would be left inside the parentheses, I believe that would be an x minus 1. So that's f prime in factored form. And if we look at this expression, well, it has 2 factors, 12x squared and x minus 1. And remember that when we multiply 2 things together, they're either positive or negative depending on the signs of the factors. So to decide where this is positive and negative, we're going to look at the values of x that make each factor 0. Those are the only places where the product could be switching sign from positive to negative or negative to positive. So we look at places where either this factor is 0 or this factor is 0. And this factor, 12x squared, would be 0. 12x squared equals 0. When x equals 0, And this factor would be 0. X minus 1 is equal to 0 when x is equal to 1. So 0 and 1 are the only x values where f prime could be switching sign, because it's the only place where these factors could possibly be switching sign. And these two numbers that we just found are referred to as the critical numbers. Critical numbers, I'm going to abbreviate numbers this way, of f. So that's just some terminology that we're learning here. So 0 and 1 are the critical numbers. Well, we still haven't decided where f prime is positive and where it's negative, but we have decided the only places where it might switch from positive to negative or vice versa. I'm going to take these two critical numbers and put them on a number line. So here's 0, and I'm going to put a little box around it because it's an important critical number, and here's 1, and I'll put a box around that as well. So those are my critical numbers, and I'm going to put some vertical lines here just to sort of separate. That breaks the x-axis up into 3 intervals, stuff that's to the left of 0, an interval between 0 and 1, and stuff that's to the right of 1. And because these are the only places where f prime could be switching sign, it means that f prime must have the same sign all throughout any one of these intervals. So for example, to the right of 1 is always positive or it's always negative, and between 0 and 1 it's always positive or it's always negative, and the same thing to the left of 0. Otherwise we would have found other critical numbers, other places where f prime could be switching sign. So right down here I'm going to write sine of f prime of x. And let's go ahead and think about what the sign of f prime is for each of these intervals. We said it can only have one sign, either positive or negative, to the right of 1. So I'm just going to pick a test number to the right of 1. Maybe I'll pick the value 2, for example. So in green here, I'm going to put my what I'm going to call my test numbers. And if I plug 2 back into the expression for f prime, it's usually easiest to plug into the factored expression. You notice that I would get 12 times 2 squared. Well, that's definitely positive because I'm squaring the x. And then I multiply that by 2 minus 1, that would be 1. That's something that's positive. So for this x value, when I plug back in, I'm thinking 12 times 2 squared. That factor is positive, and I'm multiplying it by 2 minus 1, which is another positive factor. So I'm multiplying a positive times a positive. The overall sign of f prime is positive at x equal 2, and therefore at every value to the right of 1, because we said that it can only have one sign for all x's to the right of 1, and we've decided that it has a positive sign for those values. Well, what about between 0 and 1? I'm going to check maybe the value 1/2. You have to pick something between 0 and 1. And let's go back and think about these two factors when I let x be equal to 1/2 in my expression. Well, this factor is always positive except when x is equal to 0. So when I put in a half, definitely 12 times a half squared, it has a positive sign. What about this factor? When I do a half minus 1, I'm going to get something that's negative. So now I have a positive factor times a negative factor. The overall sign is going to be negative. Now let's check to the left of 0, and you can pick any number that you want to, just be sure that it's actually a number that's to the left of 0. So maybe I'll choose the test value -1, something like that. And we'll check the sign of f prime to the left of 0. So now we're plugging -1 into this expression for f prime. This factor we said is always positive except at the critical number 0. And when I plug -1 into this factor, well, it's -1 minus 1. That's going to be negative. So I have a positive factor times a negative factor again, and that means I'm going to end up getting an overall negative product. So f prime stays negative to the left of 0. Okay, well, what does that tell us? Remember, we were looking for the intervals where f was increasing and the intervals where f was decreasing. And so this means something about our original function f. Remember from our previous page, I'm just going to put that up for a moment to remind you, at the very bottom of the previous page, we said if f prime is positive, greater than 0, f is increasing. And if f prime is negative, less than 0, f prime is decreasing. So these signs that we have on this chart for f prime sign, negative and positive, tell us exactly where the original function's graph is going up, increasing, and where it's going down, decreasing. For example, if I look at this interval of x values to the right of 1, we said the derivative is positive. That means the slopes of the tangent lines are positive, and the only kind of function that can go with positive tangent line slopes would be one that's going up. And schematically, we just draw a little arrow like this, and that means that f is increasing on this interval of values x greater than 1. And of course, f may be wiggling around, but we just draw sort of a straight arrow to indicate in a schematic way that f is going up. What about between 0 and 1? Well, there the derivative is negative. It means the slopes of the tangent lines are negative, and the only kind of curve that can go with that is a curve that is going down, that's decreasing. So if f prime is negative, it means that the graph of f must be decreasing, and schematically we denote that with just a little arrow that's going down in the interval from 0 to 1. And how about to the left of 0? For all values from minus infinity up to 0, f prime is still negative, and that means that the original function must be decreasing. So it's also decreasing from minus infinity up to 0. If you were to write out your answer to this in a very precise way, we would say f is increasing on the interval. What interval is it increasing on? According to our little diagram, it's increasing when x is greater than 1. And remember that we said that for an interval of increasing, you could put a rounded parentheses here and say from 1 onwards up to infinity, but it's technically more correct to put a square bracket there, and that's because of that technicality about how we define a function being increasing on an interval rather than at a particular point. If you put a rounded parentheses there, I think that will be okay. It depends on how picky your instructor is. For my students, it would be okay. Let's write down where f is decreasing. And you notice that f is decreasing from minus infinity up to 0. So from minus infinity up to 0, and we would put a little square bracket there. And it continues to decrease from 0 to 1. So I'm going to say for x's in here, or x's from 0 to 1. And if we include the endpoints the way I've taught you to do, notice that 0 is included in both of these. And so we could go ahead and shortcut all of that and just say it's decreasing when I get to till I get to 0, and then it continues to decrease until I get to 1. So it's really decreasing from minus infinity all the way to 1, and we can jam those two intervals together. So we would actually write it this way: f is decreasing from minus infinity all the way through 1, and I would put a square bracket at the end of 1. This would be the answer to our question, where is f increasing, where is f decreasing, and they mean give the x intervals where f is increasing and where f is decreasing. All right, we're saving parts B, C, and D until we do some discussion later, but let's go ahead and look at example 2, and we'll do part A of example 2, and I promise we'll come back and do the other parts of example 1 a little bit later on. So now we're going to go to example 2, and it's actually 2 pages ahead, so it's the 5th page of this handout. And it's the one that says example 2, so you can flip forward 2 pages, and it says f of x is equal to the cube root of the quantity x minus 1 squared. So we want to go ahead and do part A of this example, exactly the same question, where is f increasing and where is f decreasing? And again, what we mean by that is on what intervals, what x intervals is f increasing, and on what x interval or intervals is f of x decreasing. Okay, well, to do this, we have to find the derivative, because the sign of the derivative, positive or negative, tells me whether f is increasing or decreasing. So let me go ahead and rewrite f of x in a form where it's going to be easier to find the derivative. Instead of using this root notation, why don't we go ahead and use the fractional exponent notation. Let me write up here that this would be x minus 1 squared, and if I write the cube root as a fractional exponent, what exponent do I raise all this to? I raise it to the 1/3 power. Well, let's go ahead and try to find the derivative then, but before I do that, it would be easier not to use this root notation if I want to find the derivative. Remember, when we have the cube root of something squared, that's the same thing as taking that something and raising it to which exponent? It's a fractional exponent, and remember that whatever power I raise the x minus 1 to is what goes in the numerator of that fraction, and whatever root I'm taking, cube root in this case, is what goes in the denominator of that fraction. So we could write our original function this way, x minus 1 to the 2/3, same thing as the cube root of x minus 1, that quantity squared. Okay, that's a little easier form to find the derivative, so let's go ahead and see if we can find f prime of x now. And think about what rule you have to use to find f prime. Well, I really have a composition of two functions. I have an inner function, namely x minus 1, all raised to the 2/3 power. So to find the derivative, what rule do I need? I need the chain rule. So I would actually need the chain rule here. And so remember the chain rule, we do derivative of the outer, evaluated at the inner, times derivative of the inner. So I'll start with the derivative of the outer. That's really just pulling down the 2/3, and now raising this to one lower power. If I do 2/3 minus 1, that would be 2/3 minus 3/3, that would be negative 1/3. So derivative of the outer is 2/3, whatever I'm going to plug into it, raised to the negative 1/3. And the thing that I plug in is the inner function, so the thing that I plug in is x minus 1. Now I have to remember that the chain rule says, yeah, but you have to multiply by the derivative of the inner function. What is the derivative of x minus 1, though? Derivative of x minus 1 is just 1, so that doesn't really change anything in this case. So that's my derivative. Let's write it in a nicer form where it's a little bit easier to look at. Usually when we're trying to decide where the critical numbers are, where f prime could be changing sign, we don't like to have negative exponents in our expression. So I'm going to rewrite this with the 2 from the 2/3 in the numerator. The 3 is in the denominator, and I'm going to push all this into the denominator so that I can make it x minus 1 to the positive 1/3. Or if you want to, you can think of that as 2 over 3 times, and raising this to the 1/3 is the same as taking the cube root of that. So this is what my derivative looks like. F prime of x is 2 over 3 times the cube root of x minus 1. Okay, now let's think about critical numbers for this function, and remember the critical numbers are just any x values where this expression could be changing sign. And the only place where it could be changing sign, the top is always 2, so it's always positive. 3 is always positive factor, it's a constant also. And the bottom here, this factor in the bottom could be changing sign when this factor is 0. And when is this factor 0? This factor is 0 when x equals 1. So that's my only critical number. We just take this factor and set it equal to 0. So really what we did was we thought x minus 1, when is that equal to 0? That's true when x equals 1, and so 1 is my critical number. So I only have one critical number in this case. And let me just throw that on a number line like we did before. I always put a box around it because sometimes you have positives and negatives to the left and to the right of it, and it gets confusing whether this was a 1 or a negative 1 if you don't circle it or put a box around it. And remember, what we are interested in is the sign of f prime of x. We want to know, is it positive to the right of 1 or negative to the right of 1? Is it positive to the left of 1 or negative to the left of 1? And it can't change anywhere except on the interval to the right of 1 and the interval to the left of 1, because that's the only critical number we found. That's the only place this expression could be switching sign. And it may not even switch sign on both sides of its critical number. That's why we have to kind of check. Okay, well, let's check. We know that f prime is going to be either always positive or always negative for any value that I choose to the right of 1. So for a test value, I can pick anything as long as I'm sure it's in this interval. So maybe I'll try the number 2, something like that. If I take 2 and plug it back into this expression, we're just asking, is this expression positive or is it negative when I plug 2 in? Top's always positive, the 3 is always positive. If I put 2 in here, I get 2 minus 1, which is 1. That's positive, and I'm taking the cube root of a positive, so that'll be a positive answer. So I have positive over positive times positive, so I'm really thinking positive in the numerator over positive times positive. That overall sign is going to be positive. So f prime is positive not only at 2, but for all values in this interval to the right of 1. Now let's check f prime's sign to the left of 1. Maybe choose 0. That would be a nice easy test number to choose. So now we're plugging 0 into this expression, and 2 is always positive, 3 is always positive. When I plug 0 in, I get 0 minus 1. That would be negative 1. And the cube root of negative 1, remember it's okay to take an odd root of a negative number, and cube root of negative 1, I'll just mention over here, is equal to negative 1. Negative 1 to the third, cube root, excuse me, I said it but didn't write it, cube root of negative 1 is equal to negative 1, and that's because negative 1 to the third power gives me a negative 1 as an answer. So it looks like I have positive over positive times negative. So this has switched to negative, and that means that my overall sign of my expression is going to be negative. So f prime is negative to the left of 1. Well, what does that mean about the graph of the original function f? Well, we said that if the derivative is positive, that means that f has to be going up. It means you have positive slopes of your tangent lines, and the only kind of function that can do that is one that is increasing. So we just draw a little arrow there. When f prime is negative, means slopes of your tangent lines are negative. The only kind of function that can have negative tangent line slopes is one that is going down, in other words, decreasing. And again, we indicate that kind of schematically with just a little arrow that goes down. So now we found the intervals on which f is increasing and f is decreasing. Let's see if we can write them out nicely. So I'm going to say f is increasing on the interval, and if I'm careful about it, it will be increasing on the interval from 1 onwards, and I'm going to include the 1 to positive infinity. The only time we wouldn't put a square bracket here for an interval of increasing or an interval of decreasing would be if the original function wasn't even defined there. If you had, for example, a vertical asymptote there and the original function was undefined at 1. But this function is defined at 1. If I plug 1 in, looks like I get 1 minus 1, which is 0. Square it, I get 0. Take the cube root of it, I get 0. I get a number out of it, so I'm going to include 1 there. And then f is decreasing from minus infinity up until I get to 1. So on the interval from minus infinity up to and including 1. And that would really be the nice form of the answer to the question we were asked, where is f increasing, where is it decreasing? And I've indicated the intervals in interval notation where f is increasing and where it is decreasing. Okay, let's go ahead and go on to the next example, and we'll do part A of that one, and we'll come back and do parts B, C, and D of this one in just a little bit. So you need to flip forward actually 2 pages to get to example 3. So flip forward, it's really the 7th page of this section, and let's look at the function we have there. F of x is equal to x e to the minus x. So this includes an exponential function as part of my f of x. And in part A, we're asked exactly the same question. Where is f increasing and where is it decreasing? One thing you might want to think about, although this won't be important for taking the derivative, but you might want to think about the original function for a moment. When I see this negative exponent, it makes me worry a little bit. And what do I really mean by that? I could push this factor into the denominator to change its exponent from negative to positive. So this function is really x over e to the x. And you might worry that there's a denominator here that might go to 0. So there may be some x values where this function is undefined. But think about the function e to the x. Are there x values that make e to the x equal to 0? Even if I plugged 0 itself in, remember that e to the 0 is not 0, that's equal to 1. And in fact, if you think about the e to the x function, and think about its graph, y equals e to the x is a function that looks something like this. It crosses the y-axis right at the value 1, and it goes up very quickly. And we said that it was asymptotic to the negative x-axis. In fact, this whole graph is always above the x-axis. In other words, if you look at the output values of y equals e to the x, all of the y coordinates of these points, the output values of this function, are positive. So this is a function that no matter what x I plug in, positive x's, negative x's, or 0, e to that number will be something that's positive. So I just want to mention that what's in the denominator here is e to the x, and that's an expression that's always positive for every real number x. Whether x is a positive number, x is a negative number, or x is 0, this expression is always positive. And so it's never 0, and that means that this expression, this fractional expression, x over e to the x, is never undefined. So the domain of our function f, I'll just kind of jot it down up here, the domain is all real numbers. So it would be everything from minus infinity to infinity. There are no x values that would make this denominator 0, so there are no x values that would make this overall fractional expression undefined. So that's just a little bit of background about this particular function. Okay, so my f of x is equal to x e to the minus x, and what I would like you to do now is to go ahead and try to decide where f is increasing and where it is decreasing, in other words the x intervals, where it's going up and where it's going down, by using this process that we talked about, which begins with finding the derivative, then finding the critical numbers, places where that derivative could be changing sign, throwing those on a number line, and checking the sign of f prime of x to the right and the left of each of the critical numbers that you find, and deciding what that means about the graph of f. So try doing the whole process that we talked about in the previous 2 examples yourself. Pause the video, and then if you get stuck, just restart the video and we will go through it together. Okay, let's go ahead and try going through this together. We want to find the derivative of x e to the minus x. How do I do that? Well, first of all, I have to decide, are there any rules of differentiation I have to apply? And sure, it's really a product of two things. It's x times e to the minus x. So what rule do I need to find the derivative? I am going to need the product rule. So let's remember the product rule. Product rule says we do the first function times derivative of the second plus the second function times derivative of the first. It's f times g prime plus g times f prime. Okay, so it's the first function, which is x, times the derivative of the second, but that looks a little bit complicated because this isn't just e to the x, it's e to the minus x, so it's really e raised to a function of x. So I'm going to go ahead and just put times the derivative of the second, and I'll just leave that for the next step. If you can do that in your head, there's no problem. Just go ahead and write it in, but it's the first function. I'm using my operator notation, times derivative of the second plus the original second function times derivative of the first. That means the derivative of x. That's a little easier to do. Derivative of x would just be 1. So first times derivative of the second, which we haven't done yet, plus second times derivative of the first. Okay, let's find the derivative of that second function. And what rule do I really need there? It's actually rather simple, but it's still a composition of two functions. I have an inner function, namely minus x, inside the e to the x function. So since I have an inner and an outer function, what rule do I need to find the derivative? I have to use the chain rule there. So let's go ahead and use the chain rule. So this x times is just pulling down from what I have, and all of this stuff that I'm about to write is going to be the derivative of e to the minus x. And according to the chain rule, I start with the derivative of the outer function. The outer function is the e to the x function. Remember, derivative of e to the x is e to the x. It's its own derivative. So the derivative of the outer is the same function back again, because e is its own, e to the x is its own derivative. And so derivative of the outer, but now I have to evaluate that at the inner. The inner is minus x. And then by the chain rule, I have to remember to multiply by derivative of that inner. Derivative of negative x is negative 1. So that would be the derivative of e to the minus x. It's e to the minus x times minus 1. And then I still have to pull this down, plus e to the negative x times 1 would just be e to the negative x. Let me put a little line here so that we can see that that's for the graph that's coming. Okay, so what do I have? I have x times negative 1. That'd be minus x e to the minus x plus another term e to the minus x. I'm trying to decide where that's positive and where that's negative. It's not really very useful in this form when you have two separate terms. So let's go ahead and do what we did in the example number 1. When you have more than one term, you want to try to factor. And how could I factor this? Well, I could pull out a common factor of e to the minus x. Let me do that. Inside the parentheses, I'd be left with negative x plus a 1. Or we could write that as 1 minus x inside the parentheses. And I'm even going to go one step further. When I'm analyzing where f prime is positive and where it's negative, it's easier for me not to have this in a form where I include negative exponents. So I'm going to go one more step, and let me just put a little arrow here and write f prime of x then is, and I'm going to rewrite this without a negative exponent by pushing that into the denominator. It's 1 minus x in the numerator over e to the positive x in the denominator. That'd be the same as e to the minus x, 1 over e to the positive x. Now it might be easier to see what the critical numbers are. So let's see if we can find the critical numbers. Those are any values where f prime could be switching sign. And essentially that's anywhere where any of our factors, if you want to think of them as factors, in the numerator or the denominator are going to 0. Well, if I look at the numerator, it would be switching sign when the top is 0. That would be when x is equal to 1. So x equal 1 is a critical number. What about the denominator? When is that equal to 0? That would be a place where it could be switching from positive to negative. But recall, just like we talked about up here, e to the x is always positive. No matter what x I plug in, positive x, negative x, x equals 0, this expression that I have down here is always positive. In other words, it's never 0 for any value of x, and so there are no values of x where this will be switching sign. It's always positive. And there's no value of x where it's equal to 0, so it doesn't give us another critical number. So we only have one critical number, the value that makes the top 0, which is x equal 1. Let's put that on a number line. So I'm going to go ahead and put a 1 here. And now I'm supposed to check the sign of f prime to the right and the left of 1. And we know that f prime can't be switching sign anywhere else. Let me see if I can find a green pen. So let's try a test number to the right of 1. Say we try a test number of x equal 2. Plug 2 into our derivative. The numerator of this fractional expression, 1 minus 2, is going to be negative 1. That's negative in the top. And the denominator we said is always positive. A negative over a positive will have an overall negative sign. So the sign of f prime will be negative for all x's to the right of 1. What about to the left of 1? Well, 0 would be a good test number in this interval. And if I plug 0 in place of x, I'd have 1 minus 0. That's 1. That's positive in the top now. And the bottom's always positive. Positive divided by positive has an overall positive sign. So f prime is negative to the right of 1, and it's positive to the left of 1. Okay. What does that tell us? What does that mean about the graph of f? Well, if its derivative is negative, then it has negative tangent line slopes, so it must be a function that is decreasing. And if its derivative is positive, it means the slopes of the tangent lines are positive. The only kind of graph that could have that would be a graph of a function that is increasing. And so now we know where f is increasing and where it's decreasing. Let's go ahead and just write our answer nicely. I'll do it down here. F is increasing. Well, it's increasing from minus infinity all the way up to 1. So I would write on the interval from minus infinity up to, and I'll put an including 1 there. As long as my original function is defined at that 1, I can put a square bracket here. And we said the domain of this is all real numbers, so it's defined everywhere, including 1. And f is decreasing on the interval from 1 onwards to positive infinity. So on the interval from 1 to positive infinity. And again, if you wanted to put rounded parentheses here, it's a little bit sloppy, that's okay. But I know that it kind of weirds people out sometimes because they say, wait a minute, 1 is included both in the interval where f is increasing, and then you included it again in the interval where f is decreasing. Or what about that? How can it be both increasing and decreasing at 1? But don't forget that our technical definition of increasing and decreasing, we don't talk about a function being increasing or decreasing at a point. We only talk about it being increasing or decreasing on an interval. And so with our technical definition, we can include the 1 in both. It's increasing on the interval from negative infinity up to and including x equal 1, and it is decreasing on the interval from 1, including 1, up to positive infinity. Okay, what we're going to do